All right, so let us begin our first lecture by studying what I will call graph traversals. Okay, a graph traversal. So for the first few maybe lectures or few weeks, what we will do is, we will look at a graph G, V, comma, E. We can think of V being N. This is the set of vertices. E is equal to the set of edges. Conventionally, the size of V is denoted by N. The size of E is denoted by M. And at this point, the graph may be directed or undirected. And we will consider both cases as we start doing things. And so what is your typical situation? You have some kind of graph. Here's some undirected graph. Now, whatever. So here's some graph that you have. A graph traversal is an algorithm that visits all vertices and edges of the graph, right? Is a way of basically visiting all. Just like you have tree traversals, you have graph traversals. And the most famous graph traversals that you've probably seen are BFS and DFS. And BFS is breadth first search. DFS is depth first search. Okay, so what I want to talk about is, I will show you BFS and DFS again, but what I want to tell you is that BFS and DFS can be used to solve many complex problems in graphs. And that's what these, and I want to demonstrate how these algorithms can do a lot more than what you think they can do. Especially DFS can solve lots of fairly complex problems in graphs quite efficiently. We will assume, unless otherwise stated, that the graph is stored as an adjacency list. Okay, we're going to assume that the graph is stored as an adjacency list. And this is going to be important for all of our algorithms. Okay, so let me give you a review of BFS. So what does BFS do? So at the face of it, I'm just going to write out a very simplistic code over here, and then I'll give you sort of the real code. And BFS visits all vertices and edges in a specific order. And indeed, it is that specific order that defines a graph traversal. So BFS and DFS essentially use different orderings to visit. So often the way that BFS works is BFS starts from a source vertex. So S is some source vertex. And then I'll show you how BFS works on the whole graph, but BFS starts from a source vertex. And it's going to start like looking at all of its neighbors. And then it's going to look at its neighbors. And then look at the neighbors of those, so on and so forth. And the way it does that is it's going to create, I'm just going to write something here. I'll just say Q is an empty queue. right? So this is a FIFO queue, first in, first out queue. What you do is you NQ S. So here's your queue. S is going to end up in the queue. And then it's going to say while queue is not empty, it's going to dequeue.
You might want to zoom.
Session you need to.
There it is. You're going to dequeue from the queue. You're going to do something called visit, which of course I have not specified what visit is. And then you NQ all neighbors of V that are not visited. Okay, I'm going to make all of these things precise, but essentially you look for new neighbors of V that have not been visited before, and then you put them back into the queue, so on and so forth. Okay, that's what BFS is. Okay, and I don't know if anyone has seen this. Can you make a small change to this and convert BFS into DFS? Anyone? If you've seen DFS before, how do you convert this into DFS? Small change.
You can use a deck.
You can use a deck. Right. So almost. So why a deck? What is the exact data structure that you would use?
Stack.
Oh,
Use a stack.
Yeah.
Exactly. You just use a stack. And if you use a stack, then BFS essentially becomes DFS. So what is important, and what we'll see, is what is it that you do when you visit a vertex? The information that we are going to visit is going to be special. Okay. So now, let me give a little bit more specifics on the data structures that we maintain. I'm going to first tell you what BFS outputs, and then we can talk about what its guarantees are. So there is an array that I'm going to call predecessor. This is an array indexed by V. So the predecessor of V is going to store the parent of V in the BFS forest. So I'll explain this shortly. And visited is another array indexed by V. And visited of V is going to be false or true. It's a Boolean array. And well, let me sort of change this. I should say, or rooted at S, sorry. So let me say that the BFS tree rooted at S is going to be false if BFS S does not visit V, and this is going to be true if visits V. Okay, so what's going to happen is here's your graph. Now note that your graph may have multiple connected components. Let us for the moment consider the graph to be undirected. When you run BFS S, it is going to output a tree. A rooted tree with S at the root. All of these vertices are going to be present in this BFS tree. Visited is going to be false everywhere else. In all the other connected components, it's going to be false. Right? So these are the connected components. Of the graph. It's going to be false everywhere else. It is going to be true on everything in the connected component, and the output is a tree rooted at S, and predecessor is just going to denote the parent. So for any vertex here, predecessor is that parent. For this vertex V, the predecessor is going to be U, the predecessor of U is S, so on and so forth. The output of BFS S is this tree. This is BFS run from a single vertex S. Okay? Any questions about that? Does everyone see how the predecessor array is essentially storing a tree? Questions? Okay. Now let me give you the code for BFS starting from S. So I said Q is an empty Q, or is it, I should say, is a Q initialized with S. Predecessor is all null. So all the parent pointers, the parent is just going to be null. And visited is all false except visited S is true, right? And then here's the actual work. While the Q is non-empty, U is going to be, you basically DQ, you take the head of the Q, and then you're going to do a traversal. So what you say is for every V in N of U, so this is the neighborhood of U. So for every vertex in the neighborhood, we'll say if visited V is false, so that means visited V has not been visited before. First, we will say then visited V is true. And then we set the predecessor of V to be U. And that's because V was discovered from U. And then finally, step 3, I'm running out of space here, is to NQ V in the Q. Okay, this is BFS, right? So you start with an empty Q, predecessor was all null, visited was all false. While the Q is non-empty, you take the head of the Q, you look at everything in the neighborhood. So let's say that you have U over here. You have everything in the neighborhood. So I'm just going to say, I'm going to mark things that are already visited here. So U is already visited. That's why U is in the Q. Then you look at V. And if V was not visited, then you essentially make that true, and then you NQ it. Right? This is the code for BFS. Any questions about this?
Professor, I had one question.
Yes.
So in the event that vertex has more than one predecessor, what happens then? Is it like, is a list of predecessors like kept track of, or does it get overwritten?
It cannot be more than one predecessor. Like, because if you look at the way this code works, as soon as V is removed from the queue, I'm sorry, no, let me, when visited is set to be true, then the predecessor is set. Visited V is now true, so it is never going to enter this again through any other place.
Oh, okay.
Right? Because this is key, because now it's set to be true, you only get one predecessor. and the predecessor is set exactly at the time it is visited. Does that answer your question?
Yeah, that makes sense.
This is important. Yeah, go on.
And another question is, so why would you want to keep track of the predecessors if, all you're trying to do is like search for a particular vertex in, the graph?
You will see. I will tell you what you can do with the predecessors.
Okay.
And what is actually going to transpire is that the predecessor information is going to be critical in the applications of breadth first search.
Okay, understood.
Okay, so this is where it's important that this is sort of the extra information that is maintained. This information is basically just a tree.
Right.
You can interpret that as a tree.
Mm-hmm.
Actually, does someone want to say what is the special property of this tree?
It's shortest path to each vertex.
Exactly, it is a shortest path tree. In this tree, all these paths from S are shortest paths.
Mm-hmm.
Okay, that is sort of the key property of BFS. Okay, so I'm going to write something over here. This is what I'm stating here is a theorem. I am not going to prove this theorem. This is sort of a classic theorem of breadth first search. Instead, I want to use this theorem to prove other things. So I'm just going to write this as a theorem that when BFS S terminates, visited V is true if and only if V is connected to S. This means that there is a path from S to V. I'm being a little more precise here, as in from S to V, because the graph could be directed. If it's undirected, if you're confused about direction, if it's undirected, then don't even worry about this, right? Because connection now is, it's sort of a symmetric relationship. And just as an additional observation, although this is sort of fairly obvious if you look at the code, given the first part, predecessor V is null if and only if V is S or V is not connected to S. And thirdly, lastly, but most importantly, for V connected to S, the path V, predecessor of V, predecessor of the predecessor of V, so on and so forth, all the way back to S, is a shortest path, in reverse. From S to V. Okay, this is sort of the main theorem of BFS. That when it finally finishes, this tree that you get here is a shortest path tree from S. It is not shortest paths between all pairs of vertices. It's only shortest paths from S.
I have a question.
Yeah.
So does that mean BFS is bijective?
What does that mean?
As in, like, you can't have different outputs, like different trees formed?
You can. You can. Shortest path trees are not unique.
Okay.
This is not unique. I'll give you a simple example. So here's S, here's V. There are two shortest paths from S to V.
Okay.
Right? So the BFS tree, in this case, the BFS output could either be this, it could also be this. That's U1, U2. Both of these are valid outputs. Why would you get one output over the other? Well, it depends on how your adjacency list is stored. It depends on the ordering of the adjacency list.
Okay, so ordering is not guaranteed.
I mean, this could be stored in the adjacency list could be stored in an arbitrary order, and depending on the order, you would get different outputs.
Oh, okay.
But both of these are shortest path trees.
Yeah.
Picture on top and the picture on the bottom. Okay?
Okay.
Questions?
Professor, quick questions. So it doesn't matter for the directed or undirected for the shortest path?
It doesn't matter, but then, yes, it doesn't matter. This holds for any graph, but of course, when things are directed, it's looking at directed shortest paths.
Thank you.
Right? So for example, if you had a graph of this form, and the arrows were directed this way, then this is not a shortest path anymore. Right? There's actually nothing that is connected. S doesn't have a path to any vertex, in which case the output in this case would just be S as a singleton. The forest would simply be S. That's it. That's the tree, I'm sorry. The BFS output would simply be that. That's it. Because there is no vertex that has a path from S to V. No V such that there is a path from S to V. Is that clear?
Yes, thank you.
Professor, I have one question here.
Yeah.
Can we check if two graphs are identical by BFS, or you're not?
What you mean by identical? You mean they're isomorphic? You mean that they're basically the same graph? No, that's a very hard problem.
Okay.
It is known that it was actually a big breakthrough of Babai in, I think, 2016, where finally there was an algorithm that ran in what's called quasi-polynomial time. So BFS cannot be used, or at least it's not known. It's not known.
Okay, thank you.
Questions? Okay. Good. So now I want to talk a little bit about, now let me sort of, just to complete the introduction to BFS, let me talk about what BFS on the whole graph means. This was BFS starting from a source vertex. What is BFS on the whole graph? Well, this is actually quite, it's basically, you just run BFS from all unvisited vertices. So you initialize predecessor to all null, and visited to false. And then what you do is simply, for all vertices, I'll say S in V, for all vertices S, if visited of S is false, then you run BFS starting from S. So the way to think about this is that here are your connected components. It's going to pick a vertex, the first vertex. It's going to visit everything in here. After that, it is never going to call BFS from any other vertex in here. Then it's going to move to some other connected component. It's going to call BFS, and that's going to visit all the vertices. A single call for BFS in here will visit all the vertices. And then no other vertex in here will have a BFS call. And then it's going to call from here, so on and so forth. So what you get, the output is going to be a collection of trees. Not necessarily binary, where each of these is a connected component. So what you get as output is a BFS forest. Each connected component corresponds to a tree. which is a shortest path tree from the root, right? So each of these is a shortest path tree from that root, so on and so forth, right? So you get a tree for every connected component, because when you call BFS, it's of S, it's going to call this procedure, which is going to output this tree over here that we just talked about. The next one is going to output another tree, so on and so forth. This, what I have drawn here, is for the undirected case. Now, when things are directed, it becomes more complicated because connectivity is not a symmetric relationship anymore. We will discuss what happens in undirected graphs when we talk about depth first search, or DFS, which is really where things get interesting with directed graphs. Any questions about this over here?
Yeah, just to double check and make sure I'm understanding this correctly. So if we have a fully connected undirected graph, then we're only getting one tree, right?
That's correct.
Okay, cool.
That is correct. All right, now. What I would like to do now is maybe discuss a little bit about BFS further. And so for this, hang on a second, I'm just trying to just give me a second while I set up the poll for this course. I usually like to poll students in the middle. All right. Okay, so I launched a poll, but I haven't told you what the poll is about. Does everyone see that there is a poll that's launched?
Yeah.
Yeah.
Okay, so the question is, do you want me to prove this theorem? A is yes, B is no. Like B is I've already seen the proof, but A is yes, I want you to prove this theorem. Okay, all right. So most of you would like to see the proof of this theorem. So I will go ahead and I will sketch it out. But being, the devious person that I am, I'm going to make a lot of it into exercises that you can do, because many of you would like to see the proof. And guess what? I'm going to make you come up with it yourself. But I'm going to show you the basics of why this theorem is true, why this is the shortest path. And this is actually going to provide a lot of insight into basic things about proof writing and loop invariance. Okay, so let's go ahead. Before we actually do the proof, what I'd like to do is I'd like to show you. Let's do a little example, and then maybe things will start becoming clearer. Okay, so here's my simple graph here. I'm going to number all the neighboring vertices U1, U2, U3, U4, U5, and maybe there's an edge here, and there's V1, and put an edge over here, call that V2, I'll call that V2, V3, and call that W1. So here's some graph that I've constructed. All right. So I'm just going to write out what the queue looks like. Okay, so this is what the queue looks like at the beginning. So this is the head of the queue. Okay, this is the head of the queue. So initially it had S, which was visited. Okay. What's going to happen after the first loop? What vertices are going to be inside the queue?
U3, U2, U1, U5, U4.
U3, exactly. Or order differently, U1, U2, U3, U4, U5. Right? U1, U2, up to U5. Okay. What happens next? U is going to get dequeued, right? U1 is dequeued. Now it's in the queue.
U2 through U5.
U2, V1, V2.
V2.
Yeah, I'll
V1 and V2 are going to enter the queue, right? Because all of these are already visited now.
Yeah.
Okay, all right. So U1 goes away. U2 to U5 are in the queue. And then what? V1 and V2. Okay, then what? Now, U2 is dequeued. So now what?
U3 to V2.
U3, U4, U5, V1, V2. Nothing changes. Then U3 is going to get dequeued. Then what?
V3 gets added.
V3.
U3 gets added. Okay, so I'm just going to say U2, U3 get dequeued. I'm going to remove this and I'm going to put V3. What are the shortest path distances of U1 to U5? What is the shortest path distance of U1 to U5 from S?
1.
1. What about V1 and V2?
2.
2. In the graph, is there a vertex at distance 3?
Yeah, W1.
W1.
All the others are distance 2. Now here's the question. When W1 enters the queue, what needs to happen?
When V1 is dequeued,
When V1 is dequeued, then W1 goes in. When V1 is dequeued, U4 and U5 are out of the queue. Right?
right?
So when the first vertex at distance 3 enters the queue, all vertices of distance 1 have exited from the queue. Okay? I'll repeat that. When the first vertex at distance 3 enters the queue, all vertices at distance 1 have left the queue. Does that make sense? Any questions about that statement?
Does this hold as you move to further distances? If
Good
you have
question.
like distance 4.
Okay. Think about it. Good question. What is this going to always hold? Or why don't you restate? What is the statement that you're proposing?
If, as in generalizing it,
Okay, yeah, generalize it, yes.
I assume it would be something like when the first vertex at a higher distance enters the queue, all vertices, when the first vertex at distance n enters the queue, all vertices at distance n minus 2 have left the queue, maybe?
Okay. Good. So I will just, if I may point out a minor quibble. When we do algorithms and graphs, the symbol N and M are sacred. N always means edges, right? So use D. This is important.
Perfect.
This is important when you write proofs, right? Use the right notation. It's important when you write code, right? You have to name just like you name your variables properly when you write code. When you write a proof, you name your variables carefully, right? So good. So that was a generalization. When the first vertex at distance D enters the queue, all vertices at distance D minus 2 have left the queue. Is that true? So I'm gonna pause for a moment and ask you to ponder that.
If the graph is weighted, like
let's do that later. No, let's right now. It's unweighted graphs, right? If you do weighted graphs, then you have to use Dijkstra's algorithm. And you have to use priority queues. But essentially, the argument will be it's a generalization. But let's do unweighted for now.
Is it true because if you had a distance of D minus 2 in the queue still, that it means you traversed to a vertex that like you didn't properly traverse to a vertex, you kind of made a jump?
In some, yeah, that's one way of putting it. Right? So okay, hopefully you're starting to see what's going on here. And now you need to formalize this process. Yeah, are you all following? I'm just going to relaunch the poll. A is I'm following, B is I'm confused.
Oh, Professor?
Yeah.
I think I have an explanation why this statement holds.
Okay.
And it's just the simple fact that if a distance 1, still existed, there's no way you can go from 1 to 3, correct? Since each edge has like a weight of 1. Yeah. So the only way for that to be possible is if a distance of 2 was there, because you can't get to 3 from a distance of 1.
Exactly. You can't get to distance 3 from a distance of 1. You can only get to a distance 2 of a distance from 1.
Mm-hmm.
So this means that to get to a distance 3, the head of the queue would have had to be a distance 2. Right?
Correct.
But now there's an additional assumption that's buried in what you're saying. You have the right intuition, exactly. You are assuming that the queue is always sorted with respect to distance.
Mm-hmm.
Good. This is a good observation. So your argument is only correct if the queue is sorted with respect to distance.
Okay.
Right? Because what if the queue had vertices of distance 2 before distance 1?
Would that be possible?
Yeah, if you're starting at the root, would it not always be sorted?
Okay, so you're right. So good. So it would always be sorted to start off with. Mm-hmm. Will it always be sorted?
Do you need an initial condition to say that the first elements always be at distance 1?
I think it would always be sorted because you're checking if a vertex has already been visited before.
So the thing is, you're right. It will always be sorted. Now, what is the proof technique to show that?
Does it make sense that, because of the fact that we are using a queue, we're adding at one end and we're removing from the other sort of...
Absolutely, you're right. So all of you seem to have the right idea. Question is, how does one formalize this argument?
Would this not be a proof by induction?
Thank you. It's a proof by induction. Exactly. It is a proof by induction. And so what we need is the correct statement. to prove by induction, right? Is everyone following so far? You need a proof by induction. And what you need specifically is you need the loop invariant. So it's the loop invariant plus induction, or technically the loop invariant is going to contain the induction. So we're going to make a statement about the content of the Q. The content of Q with regards to distances, and I mean shortest path distances. We're going to make a statement about the content of the Q with regards to distances and prove that by induction. That is the key. And so most of you have sort of made the right observations. You're saying lots of things that are correct. The Q is sorted with respect to distance. When distance d enters the Q, then all vertices at distance d minus 2 have left the Q. And we will combine all of these statements into one sort of theorem, the loop invariant. The proof of that loop invariant will be done through induction. Once you have the proof of the loop invariant, or rather once you have the statement of the loop invariant, the proof of the theorem actually becomes really easy. Now, I want to sort of emphasize this process here, that you want to prove this theorem, but instead of trying to attack this theorem directly, which is very hard, you try to understand what is happening in the key data structure, prove properties of that data structure, which will give you the loop invariant from which we can now prove the main theorem. So I'm going to state the loop invariant here in somewhat gory detail. And then what I will do is I will use that loop invariant to prove the main BFS theorem. And then I will talk a little bit about how to prove the loop invariant, but leave that mostly as an exercise. So now I'm going to refer to this as a lemma, which I will call the BFS loop invariant. By the way, how long does class go to?
Till 1:15.
1:15?
Yeah.
Okay. Okay, so I'm going to state the loop invariant of BFS. And this is, it's somewhat of a clunky statement, it's somewhat of a long statement, but I think I like to write it this way because I think it captures what is going on in the most, let's say, comprehensive way. So what this says is, after I runs of the while loop, so this is what you're going to do induction on. You do induction on I. Induction on I. After I runs of the while loop, let d be the distance from S of the head of the Q. Right? So I'm just looking at, you've done some number of runs, you look at the Q. Now you're looking at the status of the Q. And you're looking at the distance of the head of the Q. In this case, in all of these cases, that distance is 1, but eventually it's going to be 2, 3, so on and so forth. So D is that. So I'm going to state a bunch of things here. I'm going to say the Q contains vertices at distance D followed by vertices at distance d plus 1. I'll say potentially. Okay. This is expressing this fact that the queue is sorted, but it only has two distances. It has vertices at distance d, potentially followed by distance d plus 1, and nothing else. Okay? Then I'm going to say all vertices that have been dequeued have a distance at most d. And finally, all vertices that have not been visited have a distance at least d plus 1. Okay? Does this statement make sense? Any questions about what I'm stating here? Before we get to the proof, any questions about what I'm stating here? Please, I can't imagine that this is all extremely clear. I think I'm a good teacher, but not that good. So, questions?
Is that last statement, if you had two vertices in the queue, the front two, and they have the same distance, but the second vertice has like more vertices it's connected to, doesn't that mean that the vertices, the second in-queued item, has a distance of d, not d plus 1?
Okay, good. So actually, that's a good point. So, good. So this is deliberate. There's a slight error here. And you've caught the error. Or you're almost at the error. There's something wrong about the statement, but it can be fixed quite easily.
I'm not sure if this is accurate, but I think point number 3 will hold only when you're at sort of like the last vertex of a particular depth. Because as someone just mentioned, that if you were not at the last vertex, then it is a possibility that there is an unvisited neighbor at the same d, at the same depth.
At the same distance. So d is distance, not depth.
Yeah.
Okay? Depth would be specific for a tree. Good. So this is only true if the queue has vertices of distance d plus 1, but the queue might only have vertices of distance d. Right? The queue might only have vertices of distance d. So essentially, we need to sort of reword this so that it is true for both situations.
Would that mean making 3 conditional?
You could make extra conditionals. You can try to come up with the most nicest statement. Let me come up with one. Let me state it first before writing it down. I'm going to say that let d be the distance of the head of the queue and d prime be the distance of the tail of the queue. First, d prime is either d or d plus 1. Second, the queue is always sorted by distance. Then this condition holds. All vertices that have been dequeued have distance at most d, and vertices that have not been visited have distance at least d prime. Yes? Does that make sense?
Yep.
Yeah.
So I deliberately did this because I want you to see that, this is what happens when you write proofs. You come up with a loop invariant, you realize it's wrong, and then you go back and fix it, and then you try to figure out what is the right statement. This is not obvious to come up with. By no means is this obvious. I am following the presentation in CLRS. This is the Korman, Lysis, and Revestenstein textbook, but I am deviating slightly because, I find this presentation, even though it's a little bit more verbose, kind of explains exactly what this is. So let's say that, okay, so this was actually wrong. So let's fix it. Okay, so now I'm going to state this lemma. I will write this as the BFS loop invariant. So what I can do is I'll say that after I runs of the while loop, this is equivalently set at any stage I'll just say at the beginning of step 3, because this is a loop. So just at the beginning of step 3, what is at any stage, the beginning of step 3. So after I runs of the while loop, let d be the distance of the head of the queue, and d prime be the distance of the tail of the queue. Okay, so the first point is d prime, is either d or d plus 1. Right? D prime is one of these. The queue is sorted by distance. And then we have, all vertices that have been dequeued have distance at most d. Sorry, it's written poorly. All vertices that are not visited have a distance at least d prime. This is the BFS loop invariant, and I am going to make this sort of the first exercise from today. Proving this, of course, you'll realize that it's not difficult at all once you've written this down. If you assume all of these conditions and you just look at the next step of BFS, you'll see that all of these are maintained. The queue is sorted by distance because you always insert at the end, because all the vertices that are not visited have distance at least d prime. And so when you put it into the queue, it'll always be sorted by distance. And you can easily see that whenever you dequeue a vertex, it'll always be something, at most distance d. So you can argue all of these conditions. The only thing you need to be careful is sometimes when something is dequeued, d prime changes. And when d prime changes, then you need to sort of do the right argument. I can, maybe I don't think I have time this lecture, but the next lecture I can talk a little bit about how one would prove this statement. So let me pause here and answer any questions you have about this. Is this clear?
Professor?
Yeah.
I was a little confused about when a case would arise where all vertices that are not visited have a distance of still d and not d plus 1.
So suppose you have a situation where let me see if I can if I do this carefully. It's a good point, actually. Okay, so what you're saying is that this loop invariant is itself correct. The issue one has to be wary of is what happens when when the queue only contains vertices of one distance. Then I guess technically you're right that this is probably correct, that all the vertices that have not been visited must have distance at least d plus 1. But I think that proving it through the loop invariant may be trickier, whereas proving this other loop invariant is easier. Does that make sense?
Is this like a loop invariant for like a different problem, or?
No. This is the loop invariant for the same problem. I'm just saying that. So I think that what you're saying is that this statement itself might be true.
Yeah, or like, whatever was discussed that was wrong about it, I just wanted to gain more clarity on that. I just don't understand fully why. I guess why was this wrong? I guess that's
a good question. So actually, now that I think of it, I think I may have actually painted myself into a corner, and maybe the statement is actually correct. So let's try to understand why I thought it was wrong, and let's see where I went wrong. So what I thought was going on was, suppose the queue only had vertices at distance d.
Mm-hmm.
Now, what could happen is, could there be a vertex which is not visited who also has a distance of d? And I guess that cannot happen.
That can't, right? Because if it's in a different connected component, then it's not reachable to.
Yeah, no, assume it's the same connected component, because, right? So if this had a distance of d, some vertex,
mm-hmm.
right? So this distance was d, then it must have something before it at d plus 1.
Mm-hmm.
And that vertex must be in the queue. Because if that vertex had left the queue, then this vertex would be inside the queue.
Mm-hmm.
Well, right? So at least I had the similar thought, but what seems like the major change is that what is meant by after I runs is not well defined in this first one, because there is a step in our algorithm where we've dequeued something and haven't added anything to the queue or visited anything.
Yeah, exactly. And that's why I want to say beginning of step 3.
Right. Okay.
Usually when I mean after I runs, I mean after I runs have been completed.
Okay.
Right. So I think this is a good point. So this is, I went too fast over there, and I think I made a mistake myself. So I think the claim is, whoever pointed this out, you're right, that I believe that this lemma is probably true.
Mm-hmm.
And I believe it is correct, because what I was worried about was that everything in the queue has a distance d, and there is an unvisited vertex which also has distance d.
Right.
But I guess that cannot happen.
Mm-hmm.
So this is true.
Okay.
But it is also true that this is true.
Right. Because there's a choice, right? Although one of the choices will never hold, right? Which is
exactly this is actually always going to be, at least, if I were to fix this, I would say that you could always make this d plus 1.
D plus 1, right?
Professor?
Yeah.
I think if the statement is true only if you dequeue the node after you visit it, and if you if you use the head of the queue or the dequeued element, so if you visit the vertex before it is being dequeued, then the statement is probably true.
Yeah, but you can't visit. I mean, okay, so that's why I want to make sure that I'm looking at the status of the queue at this point, not at any intermediate point. I'm looking at the entire run and then looking at what happens at the queue. If you look at the queue at like this step, somewhere in the middle, then you can get into problems. But this statement is only talking about what the queue is after I runs of the loop. Does that answer your question?
So you can after I runs, that means you're not looking at the step in between I and the first step in step 3 and the second step in step 3.
No, I don't want to. No, I don't want to look at things in between.
Okay.
Precisely for this reason, you're right that in between the statement that I made is false, but at the beginning it's always true.
Okay.
And this is going to be important, right? Because it's at the beginning that any loop invariant can be false sort of in the middle of the loop because you're actually fixing all the data structures. So what you're saying is these are like a bunch of fixes. When you do the fixes, the loop invariant is true again.
So do you have to explicitly say that in a proof or?
Oh, well, in the statement, I explicitly say that, right? I said after I runs of the loop at any stage at the beginning of step 3.
Okay. So the second proof will be more clear, right?
Yes. And I hope I can, also convince you that writing correct proofs about these things is not that easy. One has to be very careful. And, I make mistakes myself. So you shouldn't, this is by no means an easy process. But what I want to impress upon you is sorry, this is getting stuck at this weird angle here. I want to impress upon you the importance of finding the right loop invariant, because once you find the right loop invariant, the proof of this is actually going to be fairly straightforward. Because once you assume these conditions to see that the update doesn't do any, the update maintains them is actually quite easy. Okay, so now what I want to do is, we don't have much time left. Actually, we have all of 5 minutes left, which is not exactly the best time to be doing this, but nonetheless, I will do it. Let's talk about what happens when BFS terminates. We want to prove. I'm not going to prove 1 and 2. It's sort of fairly straightforward, but it will follow from 3. We want to prove that we're getting the shortest path distances correct. And this statement over here essentially will come from here. And again, the proof of this theorem is also an induction on itself, because it says that you do induction on the number of vertices that have gone through the queue. Does that make sense?
Do you mean the one that's dequeued?
I'm sorry, you do it on the number of vertices that have been dequeued. Is that not what I said? Yes. On the number of vertices that have been dequeued.
Okay.
What you essentially argue is that for every vertex that has been dequeued, this is correct. So then it is going to be true for the next vertex that you dequeue. So I'll just write a little bit over here. We only have 5 minutes left. So I'm just going to write maybe a few statements and then we can come back to this the next lecture. So let us prove that BFS outputs a shortest path tree. Right, so we prove by induction on the number of visited vertices. Right, because every time you visit, that's when you actually increase the BFS, increase the shortest path tree. So we'll prove by induction. And so the base case is trivial. Base case is trivial because, just argue about S. You just argue about the root. The distance of S2 itself is 0, and that's it. And S is already visited at the beginning. So the induction, so I'm not writing this out in full formalism, but essentially you'll see the argument. So consider V the next vertex that is visited. Now, you'll see how I'm going to use the properties of the loop invariant. Okay, so let D be the distance of the head of the queue. So and let me refer to the head of the queue as U. And D is the distance of the head of the queue, just as we had in this lemma, D. So we know that the distance of V is at least D plus 1. This is from the loop invariant. Right? We know that it's at least D plus 1, and this is critical. We also know that the vertex V is a neighbor of U. I mean, that's why V is visited. Right? Or actually that, I should say the, instead of the head of the queue is, the dequeued vertex. I mean, what this means is you have the queue over here. U is at the head of the queue, so you dequeue it, and then U had an edge to V. U was already visited, V was not visited, and that's how V is now going to enter the queue. Right? So U is the vertex that was just dequeued. And so we know that the vertex V is a neighbor of U. That's why V is visited. So we know that the distance of V is at most the distance of U plus 1, and this is exactly D plus 1. So the distance of V is at most D plus 1. It is also at least D plus 1. So that means the distance of V is exactly D plus 1. Is exactly D plus 1. Okay? And we know that by induction, the predecessor array has a shortest path of length D from S to U, right? Because U has been dequeued, and we're doing induction on the number of dequeued vertices. Hence, this path and the edge UV is a shortest path to V. Right? This path and the edge UV is the shortest path to V, and this is exactly what the tree has. And this is because U is the predecessor of V. Right? And this essentially, I've sketched out the proof, I've written it a bit messily, but this is the basic idea. And this will then complete the induction that proves that the path V, predecessor V, so on and so forth, is the shortest path in reverse. Okay, so I'll end now. In the next lecture, I will talk a little bit more about the BFS invariant. I can discuss a little bit more at a high level how one would make this argument, maybe sketch out some of the details. And then after that, I want to talk about an application of BFS, and actually an application of the BFS theorem to something, to a problem called detecting if a graph is bipartite, for which BFS is a classic application. So I'll end here and then take any questions that you have.